today's video, we are going to see the third lab component of digital design and computer organization. Design Verilog HDL to implement binary adder, subtractor, half and full adder, half and full subtractor. Now let's see half adder design. In half adder design, we have two inputs and two outputs. A and B are the two inputs. Carry out and sum are the two outputs. Carry out can be written as C out. Sum can be written as S. When we add 0 and 0, we get 0 as the output, as the sum. And when we add 0 and 1, we get 1 as the sum. When we add 1 and 0, we get 1 as the sum. But in all these three cases, we did not need the necessity of carry. But here when we add 1 and 1, we need to carry. So, we got 1 in the carry place and 0 in the sum. Now, let's represent the same truth table in the equation. While writing the sum equations, we consider the terms where we got 1 in the sum. That is, this and this one. These two places we have got 1. So, the equation becomes A bar B for this one, as A is 0 and B is 1. When we write equation for this one, we have A is equal to 1 and B is equal to 0. So, our equation will come as A into B bar. So, when we combine both of them, we can write it as A dot B bar plus A bar dot B. This will be our sum equation. Now, let's write the carry equation for half adder. Here, we have got carry as 1 in only one case. So, here both are 1. Both A and B are 1. So, we take it as A dot B. The carry out equation will become A dot B. Now, we are representing the sum and carry equation by using the logic gates. Here, the gate named X and Y are not gates. Gate 1, Gate 2, Gate 3 are AND gates. Gate 4 is an OR gate. Here, when we give the in while taking the output for gate 1, we have A is equal to A and we have taken A and B bar. B bar can be taken by using a NOT gate. So, the gate 1 will give us an output. In the same way, B is taken to gate 2 as one of the input and A bar is taken by using the Y NOT gate, and we have one more output from gate 2. When we take these two gates outputs into a gate 4's input, we get the sum equation. Here, while writing the carry equation, we take A and B as it is into the gate 3 and we get the carry out equation. Here we have written both the equations. As our equation of XOR is nothing but A B bar plus A bar B. It can also be said as X Y bar plus Y bar X in general. So we can write the sum equation as S is equal to A XOR B, and carry out will remain the same. Now let's see full adder design. Full adder design came into existence because now see, we need to add these two numbers. When we add 1 and 1, we get 1 0. That we write it as 0 over here, and when we give 1 as carry for this side. When we add 0 and 1, we get 1, but we need to add one more 1 over here. So we get 2. That's nothing but 0 over here and 1 over here. But here we have 3 inputs. We don't have any method in half adder to add 3 inputs. So full adder came into existence. Here we have 3 inputs. We can consider over here by seeing this example. These two are A and B, and this one, these two are A and B. This one is the carry out. So using full adder, we can implement these type of problems. This is the truth table to implement it. We have A and B, the two inputs, and the carry in is the carry from the previous addition. By seeing this truth table, we can analyze one more thing, that wherever we have two inputs as 1, we get the carry. That's nothing but in this example, here 2 1s are there, so we got a carry. Here there are only 1 1s, we didn't get a carry. We are implementing the same thing in the same truth table in the K-map to get the sum and the carry equation. In sum equation, when we write down all the ones in their respective places, we are not able to make any pair, quad, octet or anything. So we circle them as it is and write their names as it is without any pairing. In cout, we got 3 pairs, we write down them. In the sum equation looks similar as that of 3 input XOR gate, that is A XOR B XOR C. And the carry equation can be written by seeing these pairings, and the equation will come as A into B plus C into A plus B into C. Now we'll implement the same by using gates, logical gates. Here first let's implement sum equation. We have the 3 inputs A, B and C given from this side. We give A, B as the first 2 inputs for gate 1, which is an XOR gate. We have taken XOR gates because on simplification we got XOR in the XOR operations in between. So we have taken the XOR gate. We give AB as input for the gate 1. We get A XOR B as the output. So this output is taken as one of the input for gate 2 and Cin is taken the second input for gate 2, then the sum which comes out of the second gate is A XOR B XOR C. Now let's implement carry out equation. In carry equation we need 3 AND gates, those are gate 3, gate 4 and gate 5, and we need 2 OR gates, that is gate 6 and gate 7. We give A and B inputs for to implement this part, A and B, and we get AB out of this gate 3, and as we give A and C in as inputs for gate 4, we get A dot C in as output from gate 4. We take those two inputs, that is A into B and A into C in, which came out of gate 3 and gate 4, into gate 6 input as gate 6 inputs, and we get A into B plus A into C in as one of the output from gate 6, but it is an input for gate 7 also. And we give input B and C into the gate 5, and we get B into C in as output. We take this output also to gate 7's input, and we get C out as our equation, as our output. Thank you. In the next video, let's see subtractors.